So welcome to video 2 in this series on an introduction to projective geometry. So last time we talked about affine planes and some of the properties of what makes an affine plane an affine plane. These are also known as axioms. And today we're going to talk about something. Today we're going to move on to projective planes now, and the axioms that make a projective plane a projective plane. And remember, our motivation for this was coming from the idea of perspective, where there was this sort of point that represented a point infinitely far away where our parallel lines would eventually cross. So the axioms of projective space start off a lot like the axioms of affine space. So that is, for any 2 points, have a unique line passing through them. So that's exactly what we had for the first axiom for affine geometry. But now we're going to have something a little bit different. Remember, in our perspective drawings, we were talking about the lines that represented parallel lines. Those also crossed at some point. So I'm also going to have that any 2 lines intersect in a unique point. And then again, like affine geometry, there's 2 other axioms, and in some sense these are less important. Same with the last axiom in affine geometry. It's just more to make sure that we don't get any silly sort of useless examples. So these last 2 ones are just that all lines have at least 3 points. And number 4 says there's at least 3 points in general. There's at least 4 points in general where no 3 are collinear. So remember, all that means is that it should be that, I think that's only one now. It should be the case that only that any 3 of these points of the 4 that we can find shouldn't all lie on the same line. So if you remember last time, we found an example that satisfied the axioms of affine geometry, which had only finitely many points, and our lines didn't have infinitely many points on them. They just had only these finitely many points were the points we were counting as part of our geometry. So as a first example, we're going to take a look at another case where we only have finitely many points. So in this example, we're actually going to have 7 points altogether. So these are our points, and our lines are going to be these straight lines. Again, my drawings may look sort of curvy, but these lines are supposed to be straight. And then there's one more line here, but remember, as I mentioned last time, we don't really define point and line. And so that means that the words point and line although we have an intuitive understanding of them, they don't have to mean exactly what our normal intuition means. So in this case, I'm going to draw a circle here, a very rough circle, but this circle is going to represent a line. So I'm going to say the points that lie on this circle lie on a line. So now let's check to see if this satisfies our axioms for a projective plane. Well, any 2 points have a unique line passing through them. So certainly if you take any 2 points, you will be able to find a line and exactly one line. Remember, this circle is counting as a line for us in this geometry. So for instance, this point at the bottom and this point at the side here, they have exactly one line passing through both of them, and that's this circular line. So 1 is certainly satisfied. The next one is any 2 lines intersect at a unique point. So again, you just sort of have to stare at this drawing for a while. And if you look at any pair of lines, including the circular line, you'll find there's always one and only one point where those lines intersect. All lines have at least 3 points, so we can see if we look at these straight lines, certainly each of these straight lines have 3 points, and same with our circular line. So that axiom is satisfied. And the last one, it says there's at least 4 points where no 3 are collinear. So for instance, I could take this point, this point, this point, and this point. So these are certainly 4 distinct points in my geometry. And if I take any 3 of them, notice that there's no line which contains all 3 points. Say if I took this top one here, the middle one, and the bottom right, there's no line on which all 3 of those lay. So this satisfies the 4th axiom, and this is something, this object is known as Fano's plane. So this is an example of a projective plane which has finitely many points and finitely many lines. So now we're going to explore a bit of a more complicated example. So I'm going to define an object. I'm going to call it this sort of fancy R, P and a 2. So this fancy R here stands for the real numbers, and this P2 means projective plane. And in the next video, we're going to prove that this is in fact a projective plane. In this video, we're just going to define this object and explore what the geometry looks like. So what this is going to be is it's going to be the set of all numbers, x, y, and z, so all triples of numbers, such that we basically toss out the triple of numbers which is equal to 0. So we allow all triples of real numbers which aren't all equal to 0. And then we're going to do one more thing to the set. I'm going to say that the triple x, y, and z, these count as the same thing. So I'm going to put quotation marks around this equal sign. So this just means I'm going to pretend these represent the same object. So this is going to be the same as the triple of points lambda times x, lambda times y, lambda times z, where here I'm letting lambda be any real number. So this little weird e thing just says that lambda is in the real numbers, and I want lambda to not be equal to 0. So this is kind of a weird thing. How should we picture this object? Well, this starts off by taking triples of real numbers. So we might want to start by looking at points in R3. And in R3, one thing that we can do, if I want to find the equation of the line running through any 2 points in R3, I can give this as, say, parameterized by t. So my equation is RT. And say I want the equation of the line that passes through the points x, y, z, u, v, and w. I can write this as x, y, z plus t times u, v, w minus x, y, z. So here I'm just performing the subtraction and the multiplication pointwise. So what this means is that for any different values of t, I'll get all the points that lie on the straight line which passes through x, y, z and u, v, t. So for instance, if t was equal to 0, you could see this second term would disappear and I would just get x, y, z. And if t was equal to 1, I would have u, v, w, and my negative x, y, z would cancel out with the x, y, z over here, so I'd have the point u, v, w. And you can check if you put this in, say, some sort of graphing software, you can check that this will be a straight line in R3. Okay, so let's take a look at what happens. Say I have a point now in this RP2, so I have some triple of numbers x, y, z. Let's say I consider for some non-zero number lambda, I have lambda x, lambda y, and lambda z. And let's also consider a third point, mu x, mu y, and mu z. So first, now let's forget the fact that we're working in RP2 for a second, and let's just think about R3. So if I wanted to look at the straight line in R3 that passes through x, y, z, and lambda x, lambda y, lambda z, that would be RT equal to x, y, z plus t times, now if I go lambda x, lambda y, lambda z minus x, y, z, I'm going to get the point lambda minus 1 times x, lambda minus 1 times y, lambda minus 1 times z. And now let's one other thing I forgot to say, I want lambda to be equal to 1, and I don't want mu to be equal to 1, right? Because I want these to be 3 separate points of R3. And I also don't want, that means I don't want lambda to be equal to mu. Okay. So if we look at this equation, notice that it's possible here, because lambda is not equal to 1, it makes sense since we can't divide by 0. We know that lambda minus 1 won't be 0. So I could take t to be equal to mu minus 1 divided by lambda minus 1. So if that was the case, what I would get, RT in this case, would become xyz plus the lambda 1 down here would cancel out with these lambda minus 1s over here. And I would get a mu minus 1. So I would have xyz plus mu minus 1 x, mu minus 1 y, mu minus 1 z. And adding these together, we see that I get the point mu x, mu y, and mu z. So what this tells us is that for any choice of multiplying these constants here, if I take the point x, y, z, any choice of multiple of those points are all going to lie on the same line. The other thing to notice is that I could take t and I could let t be equal to negative 1 over lambda minus 1. In this case, over in this part of the equation, the lambda minus 1 in the denominator would cancel out with these lambda minus 1s, and I would be left with x, y, z plus negative x minus y minus z. And that's just the point 0, 0, 0. So what this tells us in R3 is that all the multiples of points are just exactly, for any given point, all the multiples of it, in this sense that we have here, all lie on the line which passes through the origin and that point. So in other words, what's happening over here in RP2 is I'm imagining that all of these points, this line, all the points on this line are representing the same thing. That's what I'm saying over here with this equality, right? I'm pretending if I can multiply any one point to get the coordinates of another by some non-zero number, then I'm going to pretend that all of these points along here represent the same point, except I'm tossing out the origin. So that means I can pick any one of these points along here in my RP2 to represent the point, or to represent all the points on that line. So one thing I could do then is I could pick all the points that lie at a unit distance away from the origin. So that means for each line, I'm going to pick its representative to be the point that has distance 1 from the point 0, 0, 0. So if I do that, right, if we think about all the points that say just lie in the, well, if I label this down here as the x, y, and z plane, if I think about just all the points that lie unit distance away from the origin in the xy plane, this is just the unit circle in the xy plane. If I think about all the points that just lie unit distance away from the origin in the zy plane, this is just that unit circle in that plane. And same thing if I thought about the xz plane. And so hopefully now you can see that this is really just a sphere, right? I can fill in more points, I can fill in circles that don't lie exactly in those planes, but they're all going to be all the points that are of distance 1 away from the origin. This actually defines a sphere in R3. But the other thing is, notice that, say, this point here, if I take the straight line passing through the origin, this point is already represented in the lower hemisphere. And in fact, for every point in the upper hemisphere of the sphere, there's going to be another point which represents the same line. So what I can do is I can actually toss out the lower hemisphere. It's already being represented, all those points are already being represented once by points in the upper hemisphere. So really what I get is just this upper hemisphere of points. And so I'm just going to take this, because this is 2D, I'm going to take this and let's look at a bird's eye view of this. So this is our picture now of RP2. And there's one other thing to observe here, is that if I have a point right on the equator of this, right, the line lying in the XZ plane passing through that also intersects over here. So that means that this point, these 2 points are identified as the same point. So in this picture down here, that means if I have 2 points which are antipodal, so they're on opposite sides of this plane here, then these represent the same point. So now, to think about the geometry of this, we could imagine walking around, say on this, somewhere along this sphere. And so looking at a bird's eye view, I could walk around, and this sort of looks like how I could walk in a normal path in 2 dimensions. However, what happens when I get to the edge, if I walk here and try and walk off the edge, I pop back out over here. So the same thing if I had, say, another path going over here. If I tried walking here and tried walking off the edge, because antipodal points are identified, I would end up walking out the other end here. So essentially, it's kind of like Pac-Man world rules, where if you try to go off the left side of the map, you come out the right side. If you try and go off the top, you come up the bottom. And so this is our picture of RP2. So I think that's going to do it for this video. In the next video, we'll actually demonstrate a proof that RP2 does satisfy the axioms of a projective plane, and quite possibly we'll get to describing a couple different types of higher and lower dimensional projective spaces. If you have any comments, questions, concerns, ideas for future videos, I'd love to hear about it in the comments section. And have a good day.